Okay, here we're going to be implementing a BST in Racket, and our goal is to focus on style in Racket. In general, in computer science, we're using computers and programming languages to model things in the real world. And we've worked with Java, which has a bunch of different ways of modeling things. And there are some practices that are built into Java that we're going to try and replicate to some extent here in Racket.
Okay, so we've got these three binary search trees here. And I want you to think about how would you represent these using lists in Racket. We have a lot of flexibility when we're working with Java in terms of modeling objects, but we don't have that flexibility in Racket. So how would you use lists? So you can pause it and try and draw out how you would do it and try and make it something that would be consistent such that you could write code that could work with this data structure represented in Racket. Okay, let me talk you through how I think about it. I'll start with the simplest node. So that's just a simple tree that has one node in it. I'm going to represent that using a list where the first thing in that list is the element. So it's that key for my node. And then I'm going to have a 3-element list where it's the key and then the left subtree and the right subtree. So I actually need to decide how I'm going to represent empty subtrees. If I have a tree with no elements, I'm going to represent that as just an empty list. So here, the key is 3, the left subtree is empty, and the right subtree is empty. And you might remember when we have sublists, we didn't have to put the single quote in there too. We actually don't. Okay, let's look at translating that same structure. So this is the key, and then this is the left, and this is the right. Let's look at how we translate that with this 6 and 7. Okay, so the first thing will be the root, which is 6. Its left subtree is empty, and its right subtree is a subtree that has 7 as the key, an empty left subtree, and an empty right subtree. So here we had the left, and here we had the right subtree. And then again within that 7 one, we had the left and the right. So hopefully this starts to make the recursive structure of these binary search trees clearer. Okay, let's do the last one. So I've got 6 as the key. The left subtree is a tree that has 4 as the key and an empty left and right. Okay, so that was the left of the 6. And then the right subtree was a tree that had 7 as the key and then an empty left and right. And in general, we're representing dictionaries when we're using binary search trees, so representing a mapping between a key and a value. But here in our Racket design, we're only going to keep track of a key.
Okay, so here I've got actually what is a legitimate binary search tree using that same representation as we just looked at. Now imagine writing code that helps you get to the tree with this that's rooted at 35. Like, oh my gosh, what a pain. But what if I drew the tree for you? And here we can see, well, we need to get, if our tree is that thing rooted at 42, we take the left tree. And then we take the right tree, and then we take the right tree. So it's the left subtree, and then the right subtree, and then again the right subtree. That gets you the node 35, or that tree rooted at 35. And you can imagine that being able to use functions like right tree and left tree can make our code way easier to write and way easier to understand than if we were trying to work with the list structure by itself. So here, when we're doing binary search trees in Racket, we're going to have all of these helper functions. So an empty BST, that'll be represented as an empty list. We can make a BST leaf, which looks just like we saw in the earlier example where we traced those out. The example with the 2-node tree, that we can make a BST with 6, and then make empty BST, that makes that empty BST for us, and then the leaf on the right-hand side. And then similarly, that 3-node tree, we could make BST with the key 6, and then we make 2 leaves, one as its left subtree and one as its right subtree. So we can see that make empty BST took no arguments, make BST leaf just took the key, and then make BST took the key, the left subtree, and the right subtree. When we call the function key on a tree, we're going to get the key of the root. So here's sort of a conceptual picture of what's happening. All right, I want you to try and write the BST helper functions for each of these. So you know the structure of these BSTs, and I want you to write the mapping between these easy to understand words with how are we actually going to modify and work with those underlying lists. Okay, so pause it here. Okay, I've got the code for you here, and that's going to be provided in the homework assignment as well. And I used first, second, and third, but you could have just used first and rest to get the same functionality. Here's a picture from Racket, and it's going to be really important that we respect this abstraction. So even though we know that make empty BST just returns an empty list, we're not going to use the empty list directly because we want our code to be really human readable.